Hello friend, I am Amir Nizami and today we are going to study analytical solution of a simply supported beam carrying point load, and it would be solved on a Matlab. So let's start. So before using the software Matlab, first we will see the brief overview that how we solve the analytical problem using hand to the simply supported beam carrying UDL load, carrying point load. So let's start. First of all, we see that this beam, it is a support, hinge support, and this end it's a roller support. So hinge support, we know that there are two reactions, one is vertical reaction and one horizontal reactions, and at the roller support there is only one vertical reactions. So total number of reaction is 1 2 3. So three reactions are there. So therefore these three reactions, we write it down here that number of reactions is equals to 3, and number of equilibrium equation, we know number of equilibrium equations how much, that is one is summation of force along y direction is 0, sum of all the forces along x is 0, and the third equilibrium equation is summation of moment about any point is 0. So this is called the equilibrium equation. So this is also 3. So degree of indeterminacy, we know that degree of indeterminacy is total number of reactions minus equilibrium equation. So 3 minus 3, that is equals to 0. So 0 degree of indeterminacy means the structure is determinate, and we give the definition that determinate structures are those which can be solved using equilibrium equations only. If it was indeterminate, then we have to make the another provision to add the compatibility conditions along with the equilibrium equations. But here this we have seen that this problem is a determinate problem, so we can directly solve it using the equilibrium equations. So first we solve means we find out the reactions. So we just apply the equilibrium equation. So summation of force along y direction is equals to 0, and upward direction we are considering positive sign. So r1 is upward, so we are just considering it positive. R2 is upward, we are considering it positive, and p is downward, so here we are considering p as a negative. So r1 plus r2 minus p, the sum of all the vertical forces should be equals to 0, so therefore it is a 0 force. Similarly, we can see here that summation of the force along x-axis should be equals to 0. So let us see all the forces along x-axis. So we are having only one reactions at this point, no another forces are acting, so therefore sum of all the forces along x-axis equals to 0. So h1 equals to 0, so we have find out h1 also. Now the third equilibrium equation is the net moment about any point equals to 0, and we are taking the positive sign for anti-clockwise direction. So if we take this about the point A, we are taking the moment, so this transverse forces would be give a moment at a distance, this is at a distance L from this point R2, so R2 into L, and this will give a moment in the anti-clockwise direction about this point A. So therefore we have considered this as a positive sign. Okay, so this is positive, and this P multiplied by this distance A, so it will give a clockwise moment about this point A. So it is negative because we have considered anti-clockwise direction as positive, so this would become negative. So therefore R2 equals to PA by L, and L means L of the beam, length of the beam, and R1 would be what? R1 would be nothing but R1 is equals to that P go that side goes that side, so it would be plus minus R2, and R2 we have seen PA upon L, length of the beam. So therefore if you will minus, we will get R1 equals to PB upon length of the beam. So we get this. So here we get the horizontal reactions, the R2 vertical reactions, both vertical reactions. So all three unknowns are known to us. So if these reactions are known to us, so horizontal was 0, so therefore we didn't require this. So only we will see this R1 reaction and R2 reactions, and load is acting P. So now we will just find the, if it is section 1 then we will find the shear force for this. So and for this section, shear force diagram for this, so both the sections, so we have plotted the shear force diagram, which is PB by L for this and PA by L, and in between it is constant. So this is the shear force diagram, and the bending moment diagram is this. Okay, so now let's start that how we will just write a code on Matlab. So let's start with that. So Matlab code, what would be the input required? So we know that there is a beam and load is acting P. So what we require? We require the length to be given, length of the beam. So in the Matlab code, we have to feed the data that what is the length of the beam. So we will write there in the Matlab that length of the beam input. We will give a command there, input, in this within the column input, enter the length of beam, length of the beam. Okay, so it will ask us to give the input, that what is it may be 6 meter or anything, we will give the input to it. Then if the length of the beam it has asked, we have given the input, then what? Then the concentrated load also it required, and at what distance this concentrated load is situated, so that's also the input. So the distance of the point load from left end support, at what distance the point load is acting, so we will give that point also. So A, we will write the input, and same in the similar manner, what is the distance of the point load. Then what is the magnitude of the P, that it is 10 kilonewton, 15 kilonewton, so we have to give the input, that what is the magnitude. Then we know that this beam is having a length where initial point we know that it is x equals to 0, and if it is x axis, so x equals to 0, and at the end x would be equals to length of the beam. Okay, so it's a continuous beam, so we will discretize it, with some part of the beam, that it is one part of the beam, 2 part, 3 part, so we will discretize in many small parts of the beam, so that we will get the coordinate of the beam. Okay, so if we give it the 10 parts, so number of points would be 11. Okay, so the number of parts to discretize is n. It will ask that how much part we want to discretize the beam, so we want suppose 10 parts of the beam, so we will give n equals to input equals to 10. Now then it will ask that what is the length of the each part. So how we will get? We will get the length of the each part, delta L, we have written that would be equals to the length of the beam divided by number of parts. So it would give the each part length, that what would be the length. Then we can write the coordinates of the beam along x-axis. Okay, so coordinate of the beam would be, it would be a start from 0, and then the increment would be every part of the beam, so first part, second part, that would add up, and it will end up to the length of the beam where it ends. And this is in green, this gives the transpose. Okay, so we will say what we will see what is the transpose in the Matlab when we will solve. So let's go to next slide. So here it's written the same, that a simply supported beam is given, and length it is asking for the input. Enter the length of the beam, input distance of the point load, what we have discussed right now. Then enter the magnitude of the point load. Then it is asking for input number of discretized part of the beam, then number of the discretization points, n plus 1, because n is the number of part. So if suppose a beam is there of length 6 meter, and we have discretized it 1 2 3 4. So n is equals to, we have given 1 part, 2 part, 3 part, 4, 5. N equals to 5 part, suppose we have given. So number of point would be, part would be 1 part, 2 part, 3 part, 4 part and 5 part we have discretized. So number of points, number of discretized points would be equals to n plus 1. How? 1 point, 2 point, 3 point, 4 point, 5 point and 6 point. So 5 parts, then it would be 5 plus 1, that would be 6 points. So 1 more than the number of parts. So number of discretized points would be n plus 1. Now length of each discretized part we have seen, that is equals to delta L, where that can be found by length of the beam divided by n. Now here it is just given in the last slide. I have just explained the beam is there, and we have discretized in several parts. So 1 2 3 4 5 6 7. So here we have taken the example n is equals to 7, which is shown here. So 7 discretized parts of a beam. Then number of points is how much? N plus 1, that is equals to 8 point. So 7 parts, each part has been shown here, and the number of points become 8. Then x is what? X would be here, that x1 is equals to 0, x2 would be equals to 0 plus this delta L1. So delta L1 we will give the data that okay, this much is the value. Then x2 would be equals to 0 plus delta L1 plus delta L2. So we will get this data. So and similarly we will get x is equals to, at final, x of n plus 1, we will get that the final would be the length of the beam, what is here considered. Okay, so x would vary from 0 to addition of each delta L, and then finally it will reach to the coordinate which would length of the beam. This is a transpose here in Matlab, we will see. So in similar fashion, its transpose is shown, that what it means. It means a vector format, that x would be here, it is explained with the number of points, number of parts, discretized part is taken as 5 and number of point is 6. So delta L will be L divided by n. So L here it has considered 1, length of the beam is 1, so 1 by 5 parts, that would be equals to 0.20. So each part is of length 0.20. So x is 0 is to delta L. So each increment, so x1 would be how much? X1 would be 0, x2 would be 0 plus delta L, that would be 0.20. Then again x3 would be 0 plus this delta L1 plus delta L2. Okay, so the sum of all, then it would be 0.40. Then x4 would be sum of 0 plus this, then we will get plus this delta, we will get this x4, and x5 similarly we will get the sum, that would be equals to 0.80 x5, and then at last x6 would be sum of all. So at last we will reach up to the total length what is given, that L of the beam. Okay, now here it's given the shear force, how to write this section in a Matlab, how we will write this part in Matlab. In analytical solution, when we are solving with hand, what we are doing, we are just writing a shear force at any section is nothing but shear force, suppose 1 would be nothing but sum of all the transverse forces along left hand or right hand side of the section. So we are considering left hand side for our ease, so it is R1, and we give the sign convention that we have chosen. So left side negative, so we will just put it negative. So we are considering this is the shear force at any section 1 and bending moment at section 1 what we are writing, that okay, bending moment at any section 1 is nothing but R1 into perpendicular distance x. So it is the bending moment. But now this part we will write in the code. How we will write in the MATLAB code? We are just going to see in the MATLAB code. So here for I equals to 1 is to n plus 1, means we have seen that a beam we have discretized of length, total length L, we have discretized in n parts. So number of points was 1 up to n plus 1 points we have discretized. So x, which was a vector format, means a coordinate. So we have chosen that x was starting from 0, x1 was starting from 0, so 0 and delta L1, delta L2, each part length was added, and then finally it would reach up to length of the beam. Okay, so that would be L of n plus 1, means at nth n plus 1 coordinate we will get the total length. So if we want to find the in MATLAB that what is the first x of 1, first value in this vector, so we will get that is equals to 0. And if we want to write that what is the last value, so if you will write n plus 1, then it will give this value L, that's the last value. And similarly in between any position, that in the third position or fourth position, any point, we can get that, we will write that x of 3 equals to, so it will give the data that what is the third position, what is the value. So a vector format is there. So for corresponding each x value, if you plot any graph that it is x and it is y axis, so where we can suppose it is the shear force or bending moment, any. So for each x, for each point x, we will get value of v and m. Okay, we'll get each value of vm at each coordinate of corresponding to coordinate of x. So the size of x, if it is of size n plus 1 row and column 1, okay, so similar size we will get for v, the same size we will get for v. So here for I is equals to 1 to n plus 1, we are just carrying it 1 to n plus 1 if x of I is greater than equal to 0. For this part, for this section, from first section is varying from, we can see that section 1 is varying from 0 to a, okay, and a is this distance, up to this concentrated load. So 0 to a, the first section is varying. So if x is greater than equal to 0 and x is less than a, so the shear force would be how much? We have written here shear force was minus r1, so it would be minus r1, and bending moment within that section m of I would be equals to how much? So it would vary from this point to this point. So for I equals to 1, I equals to 2, and it would continue. So it would be r1 multiplied by x of I. So we will get the shear force and bending moment within this section 1. Now we will go to section 2. So now let's see for this section 2 that what would be the value for this section 2. So we know that shear force at section 2 is, we calculated, so it is the section 2. So shear force would be minus of r1 and then minus, means plus p. Why we are writing? Because left side of the section it is getting downward, so we have considered our sign convention. So according to this, it is minus r1 plus p, and the bending moment within this section 2 is how much? So we will think r1 into, now the x would be from here to here for this section, it is the varying x, where x value would be from, that should be equals to greater than equal to a, and that should be less than L. So variation is this. So bending moment would be r1 multiplied by distance is x, the sectional distance is x, and this minus of p multiplied by this distance, and this distance would be total is x and x minus a. So P into x minus a. So it is the bending moment. So we will write this in Matlab code, that for this section first we will specify that section 22 is x of I is greater than equal to a and x of I is less than equal to length of the beam, where V of I means shear force within this section 22 would be equals to minus of R1 plus P, and bending moment within this section would be equals to R1 multiplied by x of II minus P into x of II minus a. So we will get this bending moment. So now let's start in Matlab. So we will code it in Matlab. So first of all, what we require to give the input. So input before that we will just write the command clc, which is the clear the screen, and write the command clear all. Now we will give L length of beam. So we are just, so what we want that the computer, the Matlab should ask us, the users, that what's the length of the beam. So we will write the command that input what's the input, that enter the length of the beam, that is L beam is equals to, it will ask in this manner. So this would be the first command. Then what it will ask, it should ask the magnitude of the load what we have applied. So P input enter the value of point load. P equals, so it will ask in this manner. Then small a, which we represented it for our convenience, that what is the distance of the concentrated or point load from left support. So we will give it input enter the distance of point load from left support. So we will write that there. So length we have given, P we have given, and A we have given. Now it's about the beam. Now let's give something discretization within this sign, percent sign. This green would not read, Matlab would not read this green line, so it will skip this line. So therefore just we have written this to our convenience, that what we are going to get. So we are going to now discretize some data. We will write according to the discretization part. So first we will write, it will ask that n, so it would ask for input, that how much part we want to discretize that beam. So enter the number of discretized parts of beam, means how much part we want to discretize, it is asking for us. So n is equals to what? We have to give the data. Similarly, from the left support, it would ask for a is equals to what. Now if you will give this n, then what is the next part? We know that we can get the length of each part. So length of each part is what? We will denote it with delta underscore L, which is nothing but, we know that is length of the beam, divided by number of discretized part n. Okay, so we can also from our remainder we can just give this, what is it, discretized we can write it in this manner, length of each discretized part. Okay, it is the length of each discretized part, delta L. And what more we can know from it? We can also get the number of discretized points would be equals to n plus 1. So number of discretized point is n plus 1. Enter. Now we will write the coordinates. That what is the coordinate? We will write it x is nothing, that is equals to 0 to delta L. So 0 is to delta L is to, last would be length of the beam, so it will vary to this. So let us see that what's the output. First we will save it. So Tude 1 SS 14 of, just for our convenience we have just saved this file. Now we will run it. Let's run to path. So what it is asking, just see, enter the length of the beam, L of beam. What we have written inside this input, within this it has just replicated it here. So we want the length of the beam as 6 meter. We have given, suppose for example 6. Then second, what it is asking, P, enter the value of the point load P. So what is the value of point load? We have given, suppose 10 kilonewton. Enter. Now enter the distance of a point load from left support A. So from left support it is asking, so we have given just 2 meter. Enter the number of discretized part of the beam, n equals to what? So discretized part, how much we want? Suppose we want 30 part for discretization of the beam. So x is equals to 0, 0.2. It is shown in the column wise, but if we will give this here now, so let's see what it will give the output. Now x would be C. Now x is in the vector format, it is in the column wise. Okay, in this column wise. Before that x was C, how the same value of x was written in the row wise 0, 0.2 and so on. But now when we have given this transpose, so what it is showing here, that it is in the vector format. So we can also get the size of this. So we can write size of x. What's the size? So size of x is 31 comma 1, means row is 31 and column is 1. It is the size of this mat x. Let's see next. So we have discretized the beam here. So now we will go to the next part. Then we will find the reactions. So let's see what is the reaction. The reaction is R1. Left side, what we have got, the reaction in the left side was P multiplied by V divided by the length of the beam. So it was the R1 into shift R2. Reaction 2 was shift P multiplied by A divided by length of the beam. So PV by L and PA by L. We get R1 and R2 there. So we have already fit the data reactions. Now what we want? We want initialize matrix size for shear force V and bending moment M. So what is the size of the shear force? So first we will just write zeros of what is size of x comma 1, what's the size, comma 1. So we want this size for the shear force, and similarly we want this size for also bending moment. Shift M. Okay, shear force and bending moment both we want to initialize this size. Now enter. We will go to the section part. Section. Before that we want shear force and bending moment. So we are going for the shear force and bending moment, and for that section 1 is the first section 1. So for II is equals to, we are just getting a loop, II equals to 1 is to n plus 1 or we know that n plus 1 we can write, or number of discretized point. We can also denote this, that shift n is equals to, we can denote it number of discretized point, control C, we can give control V. Okay, so we can also see that value this section. So number of discretized point it will give, let's see what's the value. So it is n equals to 31. We have given the small n equals to 30, so the number of discretized point is 31. So now we can also write here in the code that 1 is to n plus 1 or 1 is to capital N, both we can write. So we are writing just n plus 1 here, no matter. So for II equals to 1 is to n plus 1, what was the shear force? So V of II, means why we are writing V of II, because when the loop will take the first value, so it will consider V of 1, II equals to 1, so V of 1, so it would just go to the first value of the matrix V, and then it will just feed the data that V of I is equals to how much. The shear force was minus of R1, so it is the first value. Then shift M of II, so what would be the bending moment for this section 1 1, so that was shift R1 multiplied by X of II. Why it's X of II? Because X is also varying. So for M1, X would be having the first value from that vector format. Then for second value of the M2, it will go corresponding to the R1 into second value of the X2. So in this manner, it will find out the bending moment. Now, this section 1 we have seen that it is having a corresponding length, that what is the corresponding section length. So let's see section 1 let us see that. X is greater than equal to 0 and less than a. First section 0 to a. So let us see. We will write that if X of II is greater than equal to 0 and less than, so how we will write, and ampersand double sign, and then again X of II should be what? Less than what? A. So if this is the criteria, that if X of II is greater than equal to 0 and less than A, then the shear force would be this one minus R1 and bending moment would be this one. Otherwise, if it is not lying in this section, in another section, means other than this section 1 if it is lying in the section 2 then what would be the criteria, that X is greater than equal to A or less than L. So in this Matlab, because there is only two parts, so first part is given that if it lies in this part, then this would be the value, else we can directly write else what would be the bending moment. We will see that in the section 2 the shear force is minus R1 plus V, and bending moment is R1 into X of II minus this. So we will write here shear force V of II is what? How much? Shift R1 plus P, and it is minus of R1 plus P due to sign convention, and the bending moment would be equal to how much? Let's see, R1 into X of II. So we will give shift R1 into X of II minus P multiplied by X of II minus small a. Okay, so this would be the bending moment. Then we will write the command end for this if loop, and then again we will give end, so the loop repeats. Then what we want? We want the plot of what? Shear force. So the x coordinate would be x comma v. So we want corresponding to x, we want the shear force. So we will write shear force, and another command what we will write? Plot x comma bending moment m. So let's see. We will again run this program. So length of the beam is asking 6. Enter the value of the point load. We are taking 10 kilonewton. Enter the distance of point load from that support. We are giving 2. The number of discretized parts of the beam, we are giving 30 parts. So here it is writing unrecognized function variable b. So we have not just given. So we will write b is equals to how much? That would be equals to length of the beam, Control C, we'll just paste it here, minus a, because we have seen here that a is this much and b was total length minus this part, so the remaining part would be b. This part would be here, so this part would be here, this is b. Okay, so b is equals to length of the beam minus a. So that's why we have written that value that was not fit there, so it was giving an error. So now we have fed this data. Let's give evaluate, and now we will just go to the command final that we want this plot. So let's see what it will give. Evaluate selection. So unrecognized variable v. So again we'll go, we'll just click run. Length of the beam 6, load p is 10 kilonewton, 2 meter distance, 30 parts. So a small p, somewhere there is a small p, so it's giving the error in line 32. So let's click on it, 32. Okay, so we have just by mistake we have written a small p, but we have considered capital P everywhere, so that's why it was giving an error. So now run again, evaluate. So it has given bending moment diagram. So we have asked also for shear force diagram. Here we can see that x comma v, x comma m. So it is not showing us the shear force but bending moment diagram. What is the problem with it? So we can just solve this problem, that we will write like this, figure 1. So now enter, and for this figure 2. Now if we will just run this, then it will show both the figure. We will see. Yeah, now we can see it is a shear force it is a bending moment diagram, and it is the shear force diagram. Now what we want, the shear force diagram in the closed box. Okay, just like we have made here the shear force diagram in this manner, that it is a closed box. Okay, where this line is at 0 0, and at 0 it is going negative, and from 0 it is going positive upward. So we want a line which should join this at 0 0. So we'll write a code there in the Matlab so that it can give us that value. So let's write what we write. Line, we want to draw a line which we want to join first point of x1 to the last point of x1 by n plus 1. We can write and comma, position of y would be 0 initial also, and at the last point also 0. Okay, so now let's see this figure of shear force. So we have seen a line is joined here, but we want to make this line with a different color, not similar with the shear force diagram color. So what we will do, let's see. We will write here comma color, and if you want to write the color, you will just give, okay, comma, what the color we want. Suppose we want black, so K. Let's run it. Let's see what is the output now. So it's a K is a black color, we denote with the K, and we are just combining x0, means x1 is the first value in the x vector, so that is 0, so it is combining from 0, and xn is xn plus 1, so it would combine. Y value is first value of y is 0 here, and also first value of y is 0 here, because we are on the neutral axis, x axis, so it has joined this value. Now what more we want, we also want to show you one thing again. Let us see that we have to join this part also and this part also. So let's write that how we will join that. So let us see, just copy it, Control C, Control V. What we want to join the first one, so x of first value, and here also n would be also first value of x, and value of y-x is the first 0, y 0, and at last it is shear force at shift first value of value, so v1. So it is asking for v1. Okay, and Control C again, Control V. For the last one, what we want, x at end, and this is also the part of end, and then what we want to combine, 0, or we can say v at end, v at end value space, and then it should come on 0. So now let us see what's the result. So now it is showing that it is a enclosed box. Okay, but we want some thick line, this line should be thick, and this line should not black, but black should only this, and this should be the same with the shear force diagram which we have plotted. So this color and this color should be similar with this. So what we'll do, we will just go to plot. We will give a color also to it. By default color is blue, otherwise we will just give a color. So we'll give it color, which color we want, comma, suppose we want red color, R, red, and we want line width, suppose we want 1.5. okay, similarly Control C, Control V, comma, Control V, comma, Control V, and red color, and here also we want red, and here also we want red. So let's now see. Yes, so now the shear force diagram has been shown, but what it is showing some slant line, means some slope is there. What is the problem with it? But in actual value it is just a vertical straight line, vertical drop. It's showing some slant, some slope is there, because we have discretized it with a very small elements, means 30 parts, means 31 points. So in between value is not perfect here, correct? We can improve it. Let's see how. We will just go back, we will run it again. Enter the length, we will give the same data. Enter the value of the point load, so we have given 10. Enter the distance of the point load from left support, 2 meter. The number of discretized part of the beam we will give, suppose 120. Now see, we have just get the vertical line. So the number of discretized part we have increased, and we get the result, correct result. Okay, now we want to feed the title that it is a shear force, and it is the beam axis, and it is the diagram of the shear force diagram. Similarly it is the bending moment diagram, so we want that it is the bending moment value. Bending moment diagram is the title bar, and it is the axis of the beam. So we can go just value, so here we have let us see. So now it's showing beam axis, bending moment diagram, and the first figure is showing shear force, beam axis, and shear force diagram. So what the extra here written, we have given the x level beam axis, y level shear force, and title shear force diagram. Similarly x level beam axis, y level bending moment, and title bending moment diagram. So here we complete this video, and in the next video we will just show the bending moment and shear force diagram for the UDL, simply supported beam carrying UDL load. Thank you.